You seeing slides or a cat?
I see slides.
Okay, good. It's always a good check. All right, good to go?
Yes.
Okay. Now, just to check as well, you can't see can you see the box's screen on top of the slides? Do I need to move? No. Okay, good. Awesome. All right, well, welcome everybody. I'm Liana. I am hosting today. George has graciously handed over the reins. Today we're going to be having a guest speaker, Aaron. We've had debate over how to pronounce this. Richter. I hope I'm pronouncing that correct, Aaron.
Yeah, you got it right.
Awesome, thanks. He's going to be talking to us about parallel and distributed data science with Dask. So really excited to have him speak with us today. First, I just want to introduce some of the new people joining today and also people who have joined us before. For those of you not familiar, it's quite a collaborative community. There's a few places where you can interact, including Meetup. We have a Slack channel where there are links on the Meetup page you'll find. And there are 3 YouTube channels that you can follow along. There's these bit.ly links down here, Deep Learning TF for TensorFlow, Deep Learning Coding, where a lot of the coding challenges that we've done in the past are included there. And then this Deep Learning TF speakers, where past speakers that have spoken at these meetups, and also Aaron's session will be included in that playlist as well on YouTube. And there are GitHub repos as well, where you can find George and David Pattons and some of the other contributors' notebooks from the challenges done in the past. We also have some partnership meetups. This Machine Learning Paper Club is a meetup where they review papers, and essentially like a book club, I guess you would, but a little more academic. So feel free to find that on meetups.com and get involved there as well. And some more deep learning and data science communities, Upskills ML and Data Education DC. They support this community as well, and they're a really good resource to check out as well. So highly recommend. And then Bethesda Artificial Intelligence Meetup is another great one to check out. There's a few links here, and they have a meetup page there as well. And then finally, we have Hatchpad, which is a startups and jobs partner community where it's an online community connecting products, startups with engineers. So another really good resource if you're trying to get insights into softwares different companies use, or just getting started for opportunities. So this is a pretty growing community, so we won't do a roundtable and introduce, but I would encourage you to join the Slack channel and introduce yourself in the introductions channel and tell us a little bit about yourself and where you've come from. And yeah, I hope you enjoy today's session. In the past, we've gone through different Coursera and learning courses. The resource the DLA taps into a lot. So you can find their links here as well, and you're probably familiar with them already. And then TensorFlow is another end-to-end open source machine learning platform, which we use a lot when working on the courses and projects and challenges that we do together. And a lot of the notebooks that we've put together through Jupyter Colab, which is a Google Cloud environment that runs, very much the same as a Jupyter notebook, just on the cloud. And in the past, we have done a lot of different coding sessions together. And here are a couple of the ones that we've done: deep learning with friends, NLP stuff, time series predictions, weather predictions. So you can check out all of these repos that people have put together, the notebooks, on that GitHub link I mentioned earlier, as well as the YouTube channel, which you'll be able to see the past recorded sessions of those discussions, which are really interesting. George and Robert and David and Dimitri put together their notebooks and have presented, and often have really good discussions about and different ways of approaching the problem, which is really interesting to see. So without further ado, I will introduce Aaron to come talk to us now. He's from Saturn Cloud, data scientist there. And yeah, I'm looking forward to hearing what he has to say about parallel and distributed data science. So I'll pass it over to you.
Cool. Is my audio okay? My laptop fan is kind of screaming a bit. Hopefully that doesn't throw anything off.
You're all good. Perfect. Yeah. Lena, just make Aaron host if you don't mind. That way you can share your screen.
Cool.
Thank you, Nana.
So let's see if I got this right. Okay, so you can see my slides window, right? And nothing else.
Yes.
Okay.
Good.
Okay, cool. Okay, great. Okay, I'm ready to go. All right. So thank you very much for that intro. I'm super excited to be able to present and kind of join this community. It's really cool and it's great that it's kind of going strong even in these kind of like virtual times. So that's awesome. So the code's here if you want to kind of grab it, but I'll kind of walk through some stuff together. Quick about me is I'm a senior data scientist at Saturn Cloud. Saturn Cloud is a data science platform that's built around the Python ecosystem. And a lot of what we focus on is like accelerating data science with tools like Dask and Rapids. And we kind of abstract away a lot of the infrastructure and all the setup and DevOps stuff that data scientists would kind of need to set up clusters and machines and all that. And then we kind of make it really easy to go from just, code that you might have had on your laptop and then go to running it in Saturn and parallelizing it to clusters. So if anybody's interested in seeing more about it, I can kind of show more of the code I'm going to run through is actually in the Saturn's environment. But I'm not going to make it too much of a sales pitch. So I'm also an organizer for the PyData Miami meetup and conference. We host some meetups, and we were supposed to have a conference this year, but it went the way of all the other ones. So hopefully we'll be picking that up soon. I have a PhD in machine learning. A lot of my work was in kind of like tree models, linear models, a lot of kind of like big data type work. And so that's why this kind of fits in for me, the parallel and distributed computing side. And we'll kind of try to tie in some deep learning things to that too, because I know the kind of like the theme.
Mind if I ask where you got your doctorate, Aaron?
Sure, it's at Florida Atlantic University. So I'm based in South Florida normally. I'm out in Colorado right now, but yeah.
Thank you. I know a couple of people who they must have a pretty active doctoral program there. I know a couple of people.
Oh yeah, very, very, very active. And my PhD advisor has somewhere between 5 and 10 PhD students at a time. So there's a good group over there.
Nice.
And if you want to reach out, if you have any more questions, I mean, feel free to hop in for questions anytime during the talk. It'll be pretty informal. I am on the Slack channel, but if you want to like find me on Twitter or send me an email, you can do that too. So I want to start just with a quick kind of like just level setting of what data science might look like with Python, like if you're doing it on your laptop or your workstation. And the data science parts that I'm covering is a lot of the like data ingest, data wrangling, prepping your data, dealing with arrays, and then training some models and so forth. So this is just kind of like a quick light example of what it looks like in kind of the Python PyData ecosystem, to get some dirty, messy data, create some data sets, and then do some machine learning. And these are kind of like the tried and true packages, right? Like Pandas and NumPy and Scikit-learn. The challenge here is that a lot of these tools were built for single core in-memory work. So when data sets become larger than what fits in RAM, you have trouble. And then also if you have complex processing that you need to do, excuse me, it can be slow because you're only running in a single core. And then if you do get a bigger machine where you get your data loaded into RAM, you're still running on a single core, so it might take a while. So the idea is to kind of, what can we do as data scientists that are familiar with these tools, and then kind of extend them and accelerate them to be able to work with larger data sets and more complex computations. And this is like a quick overview. I actually am giving a talk at the Data Science Salon. It's a virtual conference at the end of this month with a more kind of in-depth view on comparing different tools to do this kind of either cluster computing or distributed computing accelerated type stuff. So if you're interested in learning about more tools, you can check that out. But today we're really going to focus on Dask, but I want to just give this brief overview and what we've seen with like the last 10 years of how data science and kind of big data have grown. They've been traditional, typically like different communities. So the Hadoop world kind of got built up in this big ecosystem of data engineers and people who are doing data warehousing. A lot of the times they would be writing code in Java and Scala. and kind of working in that world, really more for the data engineering, building up pipelines and systems. And then at the same time, we have this PyData ecosystem and this kind of scientific computing and data science world where data scientists are building models, doing complex computations, in a lot of the times, again, on a laptop or a single workstation. And so what's really exciting is the last few years have shown some tools that are really growing that kind of bridge these worlds together to be able to now do that scientific computing, heavy data science work, but also do it with large data sets and then not have to like learn a whole bunch of new tools. Like you don't have to learn Scala, or you don't have to deal with systems in the JVM and things that you maybe you're not familiar with as somebody who's used to writing it in Python code. So here's a bunch of the tools. I'd say the most mature players as far as like distributed and parallel computing are Spark and Dask. Spark does come from that kind of big data world, but it does have a Python API. And then Dask is what I'm going to focus on today. So there's that. So I'll give a quick kind of background and intro because I think it's kind of cool to see the motives for the projects and why it was created. But then most of the time will be spent on a deep dive, and it can be pretty flexible. So I have a few different like examples ready to go, and just kind of based on any feedback that you give as attendees or any questions, I can kind of tailor that. So again, feel free to make this really interactive. Yeah, so this is it. So here's a quick background on Dask. The main goal of the Dask project was to be a flexible parallel computing framework for the Python ecosystem. So its main goals are to be able to support like low level parallelism for things that maybe people write custom code for, but also to be compatible with a whole bunch of projects. And because of that low level interface, it's actually really easy to take Python code that's written in any sort of project and then parallelize it onto a cluster with Dask. And it doesn't even have to be a cluster. You can actually get a lot of performance speed ups just by running it on your laptop or your workstation if you have multiple cores. And that's kind of how I got started in Dask, is I was just doing stuff I wanted to push the bounds of what my laptop could do. And then you can extend that to larger data sizes and more computing with clusters. It was born at Anaconda. So you're not familiar, Anaconda is kind of like the leading like open source PyData company. They kind of support a lot of these open source projects. Built completely in Python with a Python API. Like I said, it's really easy to pair with other projects. Very mature in like these scientific computing communities. There's a lot of packages built on top of it. A lot of geosciences uses Dask. A lot of other different scientific areas. And so what's cool about it, it goes all the way low level to parallelizing individual functions, all the way up to having high level libraries for data frames, arrays, and machine learning. And we'll see more about that. So just as a quick, like, what does it do kind of out of the box? And I kind of arranged this from the lowest level at the bottom up to high level stuff. It can parallelize things such as any sort of like Scikit-learn model that you have, or a grid search that you were doing in Scikit-learn, or even if you wanted to kind of distribute some deep learning trainings that you were doing with TensorFlow or PyTorch, you can do that as well. It has high level interfaces though for Scikit-learn compatible API, parallel data frames, arrays, and then again, the low level API to kind of do whatever you want.
Aaron, a quick question.
Sure.
So when you say parallel, maybe you're going to get into this later, but it's not just parallel across the CPU. Does it also support GPUs?
Yes, and so so it supports GPUs by utilizing the Rapids project, which
Okay.
I will go into a little bit, and then I can also show an example of that if people are interested, because it's really cool. It's a really cool project, and Dask kind of it's one of those examples of how Dask kind of seamlessly integrates with other Python projects.
Okay.
Yeah, and we'll see that. So for just a quick, just to kind of get oriented on what these kind of like parallel data structures look like, they're not really all that complicated when you're thinking about the arrays and the data frames. All Dask is doing is wrapping a NumPy array or a Pandas data frame. So the interfaces and the APIs are going to be the same. So that's something that you might do with NumPy, you can do with a Dask array. And then it's actually under the hood a collection of these objects. So you can peek in to one of these chunks and you'll be able to see exactly a NumPy array or exactly a Pandas data frame. And I'll show you how that works too. So of course there are some things where it's like much more difficult to parallelize and distribute certain operations, but the goal is to kind of have like a complete API match between like NumPy or Pandas, as much as possible. And when it comes to like the anything else thing, and that's what's really cool about Dask, is that you can basically wrap a decorator or wrap a function around another function, and then it becomes a parallelized task graph. So this is a really simple example, and I've stolen a lot of these graphs and pictures from the Dask documentation, so I'm not going to take credit for them. I have links at the bottom for all of these things, so definitely take a look at the slides and research stuff yourself. But the key here is that, you know, there's these functions that were defined like for adding or incrementing something. And then you basically, once you wrap this delayed function around it, Dask knows that it's building up this task graph. So it's not actually going to execute that code. It's going to wait until you tell it to. And again, I'll show you some more examples of that. But what the cool part is that it goes from this really simple toy example to scaling up to an example that looks like this. And this is actually a task graph that was taken from a grid search of, you know, some sort of hyperparameter search. I don't know which model specifically, but you can see how Dask knows kind of to execute as many things in parallel as it can. It understands the dependencies between different things. So there's probably some sort of cross-validation splitting happening down here, and then a bunch of model training and evaluation, and all the way at the bottom it does some like sum or mean or something like that to get your final metric. So it's pretty cool, and we'll see this happen live. As far as like, you know, me trying to convince you why you should use it, the Python native thing is a really, really strong selling point, especially if you are kind of already working in Python and in the Python ecosystem. If you were to use another tool like Spark, you'd have to rewrite all of your code. And with that, it is part of this strong PyData ecosystem. It's supported. There's a lot of packages built on top of it, so you know that it's here to stay. You know that it's mature and it's stable, and it's really easy to scale. Like you can, like I said, you can run it on your laptop and get a lot of value out of it, and then you can bump up to a cluster if you really need that. A couple more things, maybe a little bit more cheeky points. You can really, you know, you have to write a little bit of code, but a lot of times you can just install it pretty quickly and then get going. We have some benchmarks here. This is some blog articles that I've worked on at Saturn Cloud. We do a lot of benchmarking to kind of benchmark between like single node Python and then distributed Dask or Spark and Dask. And so we see things to be like anywhere as twice as fast as Spark, up to 50 times, even more, especially when you get into like the GPU acceleration world. And that's what this bottom article here is talking about. We did like a random forest training on a distributed Spark cluster. And then we did a random forest training with a distributed cluster of GPUs. And it was like 2,000 times faster. And the bottom one, your mileage may vary on that point. So I did mention the rapids and the GPU thing here. That would kind of be a whole nother talk, and maybe if people are interested, I can come back and talk more about it. But just a quick overview on what Rapids is. It's a fairly newer project, but the whole goal of Rapids is to push all of your data science work to the GPU. So we're not talking just like neural network training and stuff with like TensorFlow and PyTorch that, you know, GPUs are pretty much known for, right? If you're going to be doing deep learning, you're going to use a GPU. And so it's kind of like a great project because, you know, if you're doing deep learning training, you have a GPU already, right? But you probably still have to process data somewhere along the way. And then you're still stuck on your single CPU core inside of CPU RAM. And so what Rapids does is take like data frames, arrays, a non-deep learning, machine learning stuff, and allows it to be executed on the GPU. So it's a much newer project, but their goal also is to have like API completeness with Pandas on NumPy and that kind of stuff. So it's really exciting. There's some really cool stuff that you can do there. And the way that Rapids works with Dask is if you think about just, you know, loading a data set into RAM. You know, my laptop has 32 gigs of RAM. I can get an instance with 60, 100 gigs of RAM, but typically your GPU is only going to have somewhere like 16, maybe 32. Are there GPUs that have that much? Maybe, you know, 16 gigs of RAM, right? So if your data set doesn't fit on that GPU memory, you're kind of stuck when it comes to Rapids. But what Dask does is it now parallelizes Rapids. So it'll actually chunk up data frames into kind of Rapids data frames. And then now you can use multiple GPUs to process kind of like big data that wouldn't normally fit on a single GPU. So that's really exciting too. More about why you should use Dask. This is just like, it's a very mature project. So it's actually pretty interesting that, you know, 5% of all Python developers use Dask. And when you think about Python, right, it's a really large ecosystem. It's not just data science. There's people building web apps. There's people doing all kinds of other stuff. The fact that 5% of those developers actually use Dask is really great. So like I said, I've stolen a lot of these screenshots from like the Dask open source documentation. And if you really want to kind of get in and get going, the best place is to look at Dask documentation. It has some of the best documentation of an open source project that I've worked with. And so there's a bunch of videos here on YouTube. They're quick, like 5-10 minute videos that will kind of just get you oriented into what Dask can do and kind of some of the different APIs and interfaces there. And I would say if you have an afternoon or maybe one day, jump into this Dask tutorial. It has everything there for you. There's a bunch of notebooks kind of just taking you from zero to understanding how to do Dask. So, and it's really great. I'd say you'd be very comfortable with thinking about Dask and writing Dask code just after an afternoon working on this tutorial. So, I'm going to show you just a few quick snippets, and I'm going to have to breeze over some stuff because, of course, I don't have enough time to explain everything. But if you want to know more, I highly, highly recommend this Dask tutorial. And then the docs, like I said, if you Google Dask, whatever, you're going to get the docs pages, and then they're very good. So this is the last slide I have actually before the code. But the key concepts to think about when you're thinking about Dask, which might be different than maybe like traditional data science or processing if you're doing Pandas or kind of other stuff, is what Dask does is it builds up a task graph and then it executes that lazily. So if you say load a CSV file, filter the data, do a group by, whatever, it's not actually going to do that until you call a function called compute or until you write the data out. Because the point is that Dask is building up a graph and it's figuring out like how to chunk the data. It's figuring out which like workers, whether that's a core or a machine in your cluster, are going to do which work. And then it only does it once you actually say like execute. That way you can kind of optimize that query plan. And then like I showed you on those diagrams is that the parallel objects like the data frames and the arrays, under the hood, they're just regular Pandas or NumPy, Pandas data frames or NumPy arrays. So those are the key things to think about as I kind of jump into the code. Any more questions just on the background of Dask or Rapids or like anything else before I get into the code?
Great introduction, Aaron. The only clarification question I would ask is how does Dask and Rapids again integrate or talk to each other? At that point, I didn't fully understand.
I see. So the way Dask and Rapids work, excuse me, is there's actually some modules inside of the Rapids projects. So one thing is if you go and look at Rapids actually, so if we go to rapids.ai, the overarching project is called Rapids, but it actually has a bunch of different packages. So cuDF is their data frame one, cuML is the machine learning one. But if you let's go to the cuDF docs because it's probably the easiest way to just see it. Let's see, so multi-GPU with Dask cuDF right here. Actually, this might have better examples. Yeah, so essentially what Dask does is, remember how I showed the fact that a Dask data frame is just a bunch of Pandas data frames in chunks? Yep. When Dask and Rapids come together, a Dask cuDF data frame in this case is just a bunch of cuDF data frames, which are the GPU Rapids data frames chunked up. And so then each of those chunks will live on like a different GPU. And then all Dask really does is handle like the task graph and then the orchestration. And then the processing is still happening with Rapids or the cuDF project.
Got it. Thank you.
Sure. Just checking the chat, make sure. Yeah, and feel free if you can put it in the chat on the Slack or the Zoom while I'm kind of peeking over at those too. Okay, cool. So so the code's all here. If you want to look at this repo, the way I've kind of have it set up is there's an environment file that'll kind of get you going with all the packages that you would need. Most of these examples you can run on your laptop or your workstation. I've kind of sized them to like not quite fit or take a long time, but that's on purpose. So because I want to show how Dask kind of helps. So if you have a bigger machine, I'm using like a machine with like 16 gigs of RAM. So if you have more RAM than that, the examples might run faster. And if you have less than that, they might run slower, but they should mostly kind of work. The only one that you can't run on your laptop is with this Dask cluster, and that's the one I'm going to show you running in Saturn Cloud. But the dependencies are pretty light in this case. See, we're just doing like NumPy pandas, and then these are a couple of Dask packages, and then a couple of machine learning packages. So I have this loaded up inside of Saturn Cloud. Just to give some context, basically what we do is we have these Jupyter server projects where you would specify a project with an image. So in this case, I created this Docker image that has all those dependencies that I just showed you. And so what we do is kind of handle all that packaging, so that way, data scientists don't have to know Docker or think about that. But you would create this kind of Jupyter server project, and I said I'm going to use it with 16 gigs of RAM and 2 cores. So I'm kind of emulating a laptop for this example. I mean, you can launch things that have up to like 500 gigs of RAM, and you can launch machines with GPUs. But just for the illustration purposes, I'm using a fairly small machine. And then we kind of just have Jupyter Lab up and hooked up there. So I kind of have those notebooks that I was showing you from the repo loaded up here, and then we can dive in and get going. So the first notebook, I'm not going to run it per se. I'm using some publicly available data from the New York City taxi data. So what this data is like individual taxi rides. So one record is an anonymized like taxi ride that somebody took. So they were picked up here, they went there at this time, they were dropped off at that time. And it has some information about like the fare amount and the tip amount and stuff like that. So it's hosted on a public S3 bucket. So I just kind of grab that with the S3FS package. And then I basically here wrote a function that will download, let's see, what is it? All of the data from 2019. So we get 12 files out of this that amount to around 8 gigs total of CSV files. And to kind of highlight the kind of like, again, like laptop exercise, I'm go ahead and just download this to the kind of local file system. So now in this data folder, I have all of these 12 CSV files. And a quick peek of, and this does it sequentially, right? So I wrote this for loop that says, for each of these file names, download it and then do it. And that takes quite a while because they're just pretty big CSV files to download. And then with Dask, I actually wrote this kind of quick pipeline here to take that list of files and then map the download file function to those. And because I have 2 cores on this machine, that only took 5 minutes. So you can look more into this Dask bag interface. I'm not going to really spend that much time there. But actually, what I do want to show you is I want to show you my resource utilization down here. So here we can see I have 2 cores and then my RAM over here. Okay, so this is to get into it. So the way that I always like to approach these things, and I think was what highlights the really cool parts of Dask, is if you start with kind of a traditional pipeline written with like Pandas and NumPy, and then write that full thing on a sample of data, and then you can then migrate that code to Dask. And what you'll see is that there's really not that much code that has to change. So right now I'm running on this machine, right, that has 16 gigs of RAM. So this is all the files that I showed you there. They're all around 600 megabytes. To load them with Pandas is just the good old read CSV function. We have to specify some data types because the CSV files are kind of messy. I don't have time to get into kind of all the details of that, but this will kind of get the CSVs loaded. Time commands here so we can kind of see everything works. Is my screen size big enough for you actually? Is the code okay? Anybody need me to zoom in?
Oh, so far so good.
Okay, cool. Just let me know. I always forget that my resolution is kind of high. Okay, so that just took a few seconds, and then we can run this command just to see. We've got, let's see, like 7 million rows here, and in memory, it's around 1.5 gigs. And so here's the data, and then we can kind of run this describe just to, all the typical stuff you would do is just kind of like exploring a tabular data set. And so we see here, what I'm going to do for the machine learning is try to predict this total amount down here. And so we can see some crazy taxi ride that's probably some sort of anomaly, not real data, that costs $600,000. Maybe somebody took a ride to LA or something, I don't know. And so basically we're going to try to use some of these other features to predict this total amount. This is like a public data set that's been around for a while. It's been used on a ton of competitions. It's just really nice for Dask examples because it's a big data set that's public. So you'll see it used a little bit, but I kind of adapted some of this feature engineering code. Again, the point isn't the details of the feature engineering. You're going to see that the model kind of sucks, but that's not really the point. The point is to kind of show how you can accelerate stuff. So now I kind of cleaned up I added some features, just basically just some time features. And then I'll specify what my features are. I think I split up, it wasn't actually even really necessary to do that. I split it up between numeric features and categorical features. Like if you were going to do a linear model, you would want to like one hot encode the categorical features and then scale, normalize, standardize the numeric features. But in this case, I'm actually just using an XGBoost model, so it's not really necessary.
Aaron, there's a couple people that were asking the chat to bump up the screen size just a little bit.
Gotcha. Cool.
Thanks.
Better. Great. Yeah, the 600,000. Yeah, it's just a ride from JFK into Manhattan, right? Okay, so we'll do our train test split, just kind of typical. This is a function from Scikit-learn, and then so now if we wanted to just kind of like see the shape of things, right? So we can see now that we split our data like, 2/3 for training and then 1/3 for testing. And this is a pretty small XGBoost model that I'm showing. Again, just for the purpose of these exercises, but you'd probably want to just increase this n estimators, and then maybe a little bit more on the depth. But there's not that many features, so you don't really need to do that so much. And so now you can see kind of my machine here is like lighting up a bit. We kind of saturated a bit of the RAM, and then now the two cores are running because I set this n jobs -1 here. It shouldn't take all that long. I don't even remember actually how long this takes. And then we can kind of like predict on our test set. And if I want to cheat, I can just go over to this one and see how long it took. Okay, it takes a minute, so it should be done soon. I saw the comment about the visualizations. Yeah, the really cool part of this taxi data set is the visualizations that people have created. It's really, really amazing. Some crazy stuff. What's interesting actually is that a lot of the visualizations have been built off of the latitude and longitude. Like, because you would actually know the exact location of somebody, where they got picked up and where they got dropped off. But then for privacy reasons, they switched that up in 2016, and the 2016 data uses more generalized zones. But the old data is kind of still out there. But it is really cool what people have done. So if you want to just like look up New York City taxi visualizations, really awesome stuff. Okay, so yeah, so that took a minute, and the model's pretty terrible. I mean, there's a big range of the thing that we're predicting, right? It went from like $0 to $600,000. So a root mean square error of 30 maybe isn't horrible, but it's still not that great. But okay, so this is kind of the thing, right? It's like I went through this pipeline. I loaded 1 month of data. Was it 1 month of data? Yeah, I loaded just 1 month of data, and I was able to kind of like do all the stuff that I would need to. So kind of the next thing would be, okay, I want to use a year of data because I want to be able to train a better model, right? And so that's when you get to kind of this mode where you're like, okay, let me just load in everything and then do everything like I was just doing it before. So if I kind of look at all these files now, I have 12 files. I only loaded 1 month. But the idea, like with Pandas, if you wanted to, you could do something like this, right? I have my load CSV function that I had. I would iterate through this, load the CSV, append it to another thing, and then combine them all together. So I'm not going to run this because if you see right now, just this session that I have loading in the 1 month of data already is occupying 5 gigs of RAM. So if I wanted to load 12 files, it's just not going to happen. It was going to take a while to kind of run this cell, and then it's going to die. So I'm not going to kind of put us all through that pain. I spent a lot of time trying to actually get this example size just right to do that. But you can try it on your own at home. And then you kind of end up like this, right? You're like, okay, maybe I shouldn't analyze all the data. Maybe I can't analyze all the data. And that's kind of where Dask comes to the rescue. I'll say though, if you do execute this on a Mac, Macs will kind of have like almost unlimited swap space. So it'll actually continue to run but it'll just be like so slow because it's swapping to disk. Anyway, so I'm going to shut down this kernel. I'm going to keep this notebook open, but I will kind of want to, and then I'll show you the Dask one like side by side if I have enough real estate, hopefully. Well, let me just show you the Dask one. I'll run through this, and then I'll show you some side by side comparisons whenever we need it. So I'm still staying on my quote unquote laptop here. I'm still on this single machine that has 16 gigs of RAM. And the one thing that you always want to do when you're kind of getting started with Dask is to initialize a distributed client with a cluster. So if you don't pass a cluster argument to this client class, it basically is going to use a local cluster, which means it's creating a cluster using the cores on your machine. So in this case, my machine has 2 cores, and you'll see here when I do this that now I have a cluster with 2 workers, 2 cores, and 16 gigs of RAM. And then you can go over to this Dask dashboard to kind of see some of those visualizations. Because I'm in Saturn, where we go behind a proxy, so I have to kind of, oh, I'm jumping ahead there. I have to kind of mess with this URL really fast, but let's see some status. So normally, if you're on your laptop, you would just click that localhost link, and it would pull this up, but I have to do that. Okay, so we're kind of doing all the same stuff. This is the same imports I was showing you before. This is my same like read CSV package with pandas. So what I'm going to show you now is how to take that kind of regular Python code that you already have and then parallelize it on a cluster. This is not using Dask's high-level data frame API, but I want to show you that you can actually do this with any function. You can parallelize anything using this Dask delay functionality. So this is the same exact function I showed you before for loading the data frame with pandas. And so I'm just saying here, this is kind of the hard way. So if you look, this is actually very similar to that for loop that I showed you that we tried to do with the other example. So actually, I will show them side by side. So if you were thinking about like wanting to just load multiple files with pandas, you would iterate through each file, load it, and then concatenate them all together. This is very similar when I want to do it with Dask. I'm gonna go through each file that's listed. Do this. I'm going to go through, so it's the same kind of list of 12 files that I have. I'm going to iterate through them. But if you notice here, the difference is I'm wrapping this load CSV in delayed. And what this is telling Dask is saying, don't actually execute this function now, just add it to my task graph. So what it's going to do, it's now going to create these delayed objects, and I'll show you. So I run this thing, and it only takes just like a second or a couple seconds, because again, it's not actually doing anything. It's Dask kind of figuring out what all the files are, what all of your delayed calls are trying to do. And it actually normally shouldn't even take that long. Hopefully this works. Okay, so essentially, you know, if I were to run this would take minutes and not execute. And then this right here is a helper function from the Dask data frame kind of API. And it's going to take these delayed objects and convert them into kind of a Dask data frame. So here I'll show you. It's a lot easier to see. I'm going to go ahead and kick off some of these cells just so we can see it going. But now you see this data frames list is not actually a list of data frames. It's a list of delayed like objects. And so what happens is if I peek into one of these objects and I call this compute method, it's like now it's actually going to execute whatever's inside that delayed thing. And in this case, my delayed thing was just a load CSV with pandas. So it's going to return a pandas data frame. So now if I run compute on this like first thing, now I get my data frame like I was used to seeing before. If I look at my type, it's a pandas data frame. But now this taxi object I created was saying Dask data frame.from delayed. So this is from a list of delayed pandas data frames. So we're kind of stitching together the Dask data frame distributed kind of thing. And so now you can see here, and let me bring this over because we don't need the other notebook. Now you can see here that this is just kind of like a pointer to a bunch of data frames. It's a Dask data frame with 12 partitions. Each of those partitions is one of those single files that I read, and it's a pandas data frame. So now when I call this length thing, this is actually an action that's telling Dask to go ahead and do something. So up until this point, Dask didn't actually read or execute any of those pandas read CSV commands except for this one that I just did here, just on the first one. But now what this is doing is it's figuring out that task graph and it's actually computing the length of each chunk in parallel, and then it's going to return it together. So if we look at our dashboard, we can see just exactly that happening. So this shows us kind of each row here is each of my CPU cores. It's more exciting when you have more cores, but right now I just have 2. So now it's actually doing this from delayed kind of length, excuse me, in parallel on 2 things. And so we can go over here to the graph here, and we can see kind of the graph that it's building, right? So it's doing, oops, sorry about that. It's loading some stuff. So these are finished. It's executing some more stuff in parallel, and then it's computing the length of stuff kind of independently. And then, because the length is really easy to compute in parallel, right? You just compute the length of each one, and then you sum it at the end, and then they'll give you that sum all the way here down at the end. So I'm going to let that run. It'll spit out the length in a second. But this is kind of the better way. So that was the illustrating. I kind of wanted to show you that you could just wrap any function that you already had with Dask delayed and then parallelize that. But Dask data frame, like I said, matches a lot of the API from Pandas. So in this case, we can actually just do DD, which is my Dask data frame that I imported, and I'll say read CSV. And in this case, now I can use that glob syntax, which means go into my data folder and load everything that's 2019 dash whatever. So this will load 1, 2, 3, 4, 5, all the way up to 12. So this is something that Pandas can't do because it can't, when you say read CSV, Pandas expects 1 CSV file, right? Dask is actually going to know that these are all individually different files, and then it'll create that same exact Dask data frame structure that we showed here, except it kind of does it automatically for you. So then when I look at this taxi object now, it's a Dask data frame, and in this case, it actually created more partitions. So more partitions in this case is probably good because that means it can parallelize this, all of the operations that it's doing a little bit faster. So it'll actually read a different chunk of the CSV file. And so I'm not going to run this again, but that's running that same length command, and we can see that it returns exactly the same length as I showed before up here. So it's pretty cool. Like we're now operating with 84 million rows from an entire year of taxi rides all in New York City, all on your laptop. I know I'm in a cloud machine, but let's pretend it's your laptop, right? And it doesn't actually fit into RAM. One CSV file took 5 gigs of RAM. And so, you know, Dask will load things that it needs to when it can, and then it'll evict the memory when it's done with that thing, and then it'll kind of keep going. So it kind of, it figures all of that stuff out for you. And in this case, we can see, this is just computing the memory usage. So now in total, it's actually 16 gigs of RAM in memory. So it barely doesn't fit. But then as soon as you wanted to like train a model or do some intense computation, that memory is going to balloon and then it's just going to blow up. Yeah, right? They should write everything in Dask. So this takes a long time to do this describe. I'm not going to kick it off. You see it takes 17 minutes because this is actually pretty intensive if you think about what goes on in this describe command. So it's going through each individual column. It's doing a count. That's really easy. Mean isn't that hard to distribute, right? Because you can kind of compute the individual means on each chunk and then kind of combine that together. But then when you think about percentiles, that can get really expensive to compute in parallel because you kind of have to sort your data, right? And so you kind of have to maintain all that communication. So long story short, it takes quite a while. It'll work. And what's really cool is that it'll still work on your laptop. If you try to do this with Pandas, it would blow up. And a lot of things would just kind of blow up. But, you know, it's slow, but if the only hardware you have access to is what you have, you can use Dask and kind of at least get some answers. There's a question here on the meaning of vendor ID. The vendor ID here is, I believe, the technology vendor that the New York City Taxi Commission used to collect the data. So it's not all that meaningful for the machine learning exercise, and I'm not going to use it for there. Rate code ID, I'm not actually sure what that means. Oh yeah, so a lot of these are categorical, but they're kind of integers. I guess that the New York City kind of, when they create a data set to kind of make it smaller to load. So technically the vendor ID is a categorical, like it's a 1 and 2, but it means different categories. But again, we're not using it in the machine learning, so it's not all that important. So there's another question here for why would describe not just use random sampling for the percentile calculations? And that's a great question. And you can. I mean, it could, but the kind of pandas out of the box .describe method is written in one certain way and it doesn't do that. I believe Dask does have kind of approximate percentile functions to where if you really had a gigantic data set and you didn't want to do all that sorting, you can definitely do that. A lot of the distributed kind of platforms you see when it comes to percentiles will do some approximations. Another question here is, would Dask run in a Colab notebook? Absolutely. So Dask is Python, right? So actually, I haven't used Colab all that much. Does Colab give you like multiple cores, or is it just a single core thing? I know it can give you GPUs, but anybody know?
Good question. I think it's a single one.
Okay. So if it's a single core, you could run Dask, but you wouldn't get anything from it because it would just have one chunk and it would kind of just be doing the Panda stuff anyway. On your laptop, you'd probably get a little bit more, or on some sort of cloud machine on AWS or something, you can just get something with a bunch of cores. And that's kind of usually the way that we'll tell people is that, like, get a big machine with 100 cores and 500 gigs of RAM, run it there, and then if you need to, you kind of run in a cluster.
And Colab has a pro version, Aaron. I'm pretty sure that one has probably more hardware in the back end.
Gotcha.
Instead of the free one that you get out of the box.
Okay, gotcha. And shameless plug, Saturn has machines that you can launch too. We do have kind of like a hosted platform that's in beta right now where normally you would have to install it into your AWS account, but we have kind of this hosted platform where people, similar-ish to Colab, where you can kind of just sign up and get going, and then you add a credit card for the billing. Okay, so we just saw on the chat someone said Colab is 2 cores. So yeah, so you can get a little bit. You can kind of do it the way that I'm doing here. But with 2 cores, you get some, but you don't get all that much. So you kind of want a little bit more to get more power out of it. Okay, so moving on. So this next part is actually going to be exactly the same as Pandas. So you can trust me on it. You can check the notebooks later, but this feature engineering code is exactly the same because it matches the Pandas API. So the difference here is when I run this on my data frame, you notice that that executed instantly, even though there's like a lot of data there. It's because, again, Dask is doing stuff lazily. It's building up a task graph. It hasn't actually done anything yet because I didn't tell it to. So when I call this head function is when it will. It'll actually just run that code on my first chunk of data, and then it'll show it for me. So like, here's all of the features that I just created. And again, this part is the same, kind of the features that I'm using. And then notice here that the imports are slightly different, right? So instead of Scikit-learn model selection, I'm doing Dask ML model selection, train test split. So the API is the same for a lot of this stuff, except it's now distributed across your machine or across a cluster. So again, I'm going to run this. Didn't do anything yet because it's building up task graph. And then there's one thing that's useful, and we'll see it in the cluster example, is you can do this thing called persist, which means it'll actually like checkpoint your graph. And it'll execute all of the stuff that you've built up for it up until this point, and it'll persist and save that stuff into memory. I can't run it here because I actually don't have enough memory to hold the data, right? If I did, I wouldn't need Dask, right? But in this case now, I can run this XGBoost code and then run it. I'm not going to run this now because it's going to work, but it's going to take forever. And you know, it's going to produce the same kind of output that we saw like on the laptop version, except you know the metrics will be different because now we're using like 12 times as much data as we were using on the other example. But this is just kind of to show you that the API is very, very similar. Okay, moving on to the next one. Okay, so this is now running it on a cluster. The code is pretty much exactly the same as this Dask laptop version. That's kind of one of the cool things about Dask is that you can parallelize, you can prototype onto your laptop, and then if you really need the power of a cluster, you can kind of pretty seamlessly move up. This chunk here is the one proprietary thing that is going to be in part of this example, just because you know it takes a lot of infrastructure and stuff to actually host a cluster. Right? You can launch a single machine with EC2 or Colab fairly easily, but when now you talk about a cluster of machines all having to have like the same packages or the same versions of your Python packages, infrastructure, kind of communication and all that stuff. I'm running this now with Saturn's Dask cluster kind of interface. So if you wanted to see like the UI version of it, you would kind of create a cluster here. You would say, you know, what kind of machine should my worker have? How many workers do I need? That kind of stuff. But here I'm kind of doing that from the API. So now instead of my little 16 gig machine, I'm now running a cluster of 10 machines that have 64 gigs of RAM each. So, I mean, you could do this with like the 500 gig machines if you really wanted to go crazy. But this is just like an example. And so Saturn, we kind of make it easy for you to do that stuff. Technically, you can launch clusters yourself, like if you already have like a Yarn installation with Hadoop, or if you had, you can actually run it with Kubernetes as well. But this is just kind of an easy way to do it right here. And so now this dashboard is actually hosted right here on this link. So it's kind of the similar dashboard that we were looking at before for the local version, but now we're running this on the cluster that has 600 gigs of RAM and 10 workers. Okay, so this code is all like pretty much the same. I kind of already ran some of this stuff for you, but if you notice, like calculating this length, the memory usage, and then this describe, remember that describe before took 17 minutes to run on the single machine. This case only took 1.5 minutes. If you had a bigger cluster, you know, you could do it even more.
How many computers do you have in this cluster, Aaron?
This is 10.
Okay.
Yeah. So this is all the same code. There's really not really all that much different to run. The one difference here is that I actually can now run this persist command. So what this persist command does is it'll perform all of that CSV loading, it'll perform all of the feature engineering, and then it saves that into memory on the cluster. So I already ran this. It took about 1 minute for all of that to process. But we can see here, this top left graph is showing the amount of memory that's stored across your cluster. So now it's showing me that it's storing 23 gigs on my cluster because I decided to persist that. So the data set was like 16 gigs. There's probably some more overhead stuff that's going on there. And if we go to like, I think system maybe. Oh, we can kind of watch that. I think it's workers actually. So here, so we can see like all of my individual workers, and they're all using like 2 gigs of RAM. So they all have chunks of the data on each of the workers, and they're not doing anything right now. So the CPU is at nothing. But I'm gonna make it do stuff now. So this length, if we run this now, it's super quick because all that data is loaded in the cluster. It's loaded in RAM. It's super fast. The one where before I did the persist, it still took about 1 minute because what I had to do is load all the CSV files into RAM, compute the lengths, and then do that. Whereas now, once it's persisted, all those CSV files are already loaded into RAM. And then now this describe is a whole lot faster too. So I'm actually going to kick this one off and show you the kind of graph running. So now we can see that the CPU is starting to spin up a little bit. We can see that tasks are starting to run now. So what's cool about this dashboard is that you can see the actual individual functions that are running. And so we can see that there's some minimum aggregation that's like waiting because probably some of the other stuff is running first. And then like, you know, if you had arbitrary functions, you would kind of see them running. If you did a grid search, you would see all the different like model fitting and training happening. Sometimes I kind of just like stare at this because it's pretty mesmerizing to see all the stuff happening. It's pretty cool. And all this red here actually is indicating shuffling. And that's probably because of our percentile stuff. Shuffling means it has to send data between different workers. And that's when it gets really expensive. If I was doing something like a length, I could compute that all in place on the different workers because I could just compute the length of each chunk and then combine them together. In this case, because of the percentiles, you kind of have to do a lot of shuffling. But then you could kind of like click into these, see a little bit more kind of like profiling on the different like the different operations that you were doing. I won't kind of spend too much time, but you can really see, like if you had a really intense application that was taking a long time, you could debug them pretty well. And so after this, I'm just going to go ahead and kick off the machine learning part. So, okay, you're getting a sneak peek already, and you see the model is terrible and that it takes 2 minutes to train. But now we can see down here at the bottom, it's now doing this XGBoost training in parallel. So XGBoost has an interface already for doing parallelized training. What Dask does is it hooks into that and then sets up an XGBoost worker on each of the Dask workers. So now Dask is training on the data that's available in each chunk on each of the workers, and then it's going to do it in parts. And XGBoost is kind of like an iterative algorithm, right? So you're going to get parallelization for a time, and then it's going to have to come back, and it's going to parallelize, and then come back. If you were doing something, and we have examples of this, like a grid search or like a random forest, you can get some really, really drastic performance improvements because those are kind of the quote unquote like embarrassingly parallel type tasks to do. Cool. All right, so I just want to do a time check and see kind of where I am at time. Oh, so I think someone's muted if you're talking, George.
Sorry, I was muted. Yeah, sorry.
Yeah.
Saying we have 30 more minutes if you want to keep going, but we have some questions in the chat when you get a moment.
Okay, great. Yeah, and I don't think I'll have 30 more minutes of stuff, but I have some kind of cool stuff I can just hop around and show you some things I've been working on. I see another question here.
Yeah, let's start with Martin. He's asking, what is the target customer for Dask? What situation? And
Okay, cool. Yeah, I think I missed some of the questions. So, so the target customer for Dask, I would say target is people who do scientific computing or data science with Python. I think is the main target audience. I would say partially like data engineers too, who are very kind of like Python oriented, who are doing a lot of Pandas stuff. Dask would be a great fit for that as well. And the reason I say that is because of how tightly coupled Dask is to the Python ecosystem already. And like I showed you that you can kind of slap decorators on functions and then parallelize it and then extend to a cluster. And the Dask open source package has some stuff where it's pretty easy to kind of get going on the cloud. And then kind of the mission of Saturn Cloud is to just kind of eliminate a lot of that infrastructure stuff and to just basically get a data scientist who's used to working on their laptop on now running on clusters of machines and increasing kind of your performance by multiple factors.
got it. Then in your Dask API, you showed us the right way or the better way to do your data science or your data analysis. And you used similar or analogous libraries as Scikit-learn. And David is asking, is that a compatibility, like a one-to-one compatibility with Scikit-learn and Dask, or is Dask only supporting a very small subset of Scikit-learn as of now?
Yeah, that's a great question. So there's a Dask ML package. So if we just go to like Dask ML, you can kind of see some of this documentation. So I'll say I wouldn't say there's definitely not 100% coverage. Like Scikit-learn is a massive package. There's a lot of stuff that it does. And there's some stuff in Scikit-learn that's not parallelizable. So the stuff in Scikit-learn that's kind of single-threaded and not parallelizable, the Dask ML package kind of rewrites it, but then uses the same API. So like I showed you the kind of train test split, right? The Dask ML has a native train test split function that matches the API of Scikit-learn, but under the hood it's a slightly different implementation because it needs to be distributed.
And is it
some, yeah.
Oh, sorry. So the second part, kind of my question there was version numbers. Like, so, the Dask ML is a kind of a replacement for some of that Scikit. What version is it actually compatible with or replacing? Does that make sense? What I'm saying?
Sure, yeah. And I think that changes a lot with each release. And so each of these packages, and this is when you kind of get into this, some of the challenge of the Python ecosystem is that each of these packages have specific other versions of the other packages that they're compatible with, right? So I think if we were to go to Dask ML on GitHub, let me see if I can do this. Let's see if I can look at this code real fast. So if we go to the setup of the Dask ML package, we can see that here it says it requires Scikit-learn greater than 0.23.
Okay.
Yeah. So it's, and that'll depend on the version of Dask that you're installing. Like right now, this is the master branch, but it fluctuates. So that's the thing. You're gonna have to look at, like if something in the newest Scikit-learn version breaks Dask, they might have to pin a lower version with the Dask ML. But again, this community is pretty active, so they're good at like keeping up with that stuff.
Okay.
And so I talked about the parts where like Scikit-learn's implementation is single-threaded, like it has to be parallelized. Dask rewrites that. But there's a lot of stuff in Scikit-learn that has an ability to be parallelized. So a really easy example is a grid search, where you're running a bunch of different models at the same time, right, on just different slices of data. So you can parallelize that. A random forest is a good one too, because it's kind of like an embarrassingly parallel model, right? You can send different chunks of data to different parts of different trees in the forest, and then those will train in parallel and they'll come back. So Scikit-learn already has kind of that job-lib interface. So here, like this job-lib backend where Scikit-learn will parallelize to all the clusters on your single machine if you have it. And if you want to push that to a Dask cluster, you would kind of just run this, and then Dask actually knows under the hood to now parallelize that work. And you can see some of the examples later. Another interesting one is this parallel Metaestimator thing. So there's this parallel postfit class, which will actually wrap a Scikit-learn model. So the workflow here is that you have a pretty small data set that you're just going to train with Scikit-learn. You don't need Dask for it. But then you need to do like large scale inference. And you have like a bunch of data coming in. And then you would parallelize the inference or the scoring. And in this case, Dask kind of handles that part. Essentially what Dask will do is just put that model into different chunks across your cluster, and then it'll load in different chunks of data and then do that prediction. Whereas if you try to do that with Scikit-learn, it would just take a long time because it would have to just do that single threaded type stuff. And then it has a lot of other stuff. It has some integrations with like Keras and TensorFlow and PyTorch. In this case, using this Scorch package, you could do like a, let me show you this one. The TensorFlow one is better. Where if you wanted to do like hyperparameter optimization, you could then kind of utilize that. You know, it would still be doing the training on an individual like TensorFlow thing on your individual GPU. But then if you had multiple machines, you could then parallelize that.
Hey, Aaron, I had a question. When you're creating your Dask data frame, is there an option to give it a hint to tell it how you would like it to partition the data?
Yes, absolutely. So actually, probably just the documentation is going to be the good place to show you that too. So when you're loading, let's see, no, that's not, oh, that is the one I want. Okay. So let's say you were to, let's do like, Pandas, yeah. So let's say you had a Pandas data frame that you already had loaded and you wanted to put that into a Dask data frame. You can specify the number of partitions that you wanted. So like how you wanted to chunk that. When we were doing that delayed example, right, when I did that for loop, that is basically each item in that for loop became one of my partitions. And then afterwards, like, you know, if I was doing the 12 months of those 12 CSVs, if those 12 months were still chunks that were like too big that I wanted more partitions, I could call this repartition command. Repartition somewhere, here we go. This repartition command, and you can tell it now, increase the number of partitions just to increase the parallelism. So it is very flexible how you can partition your data. And that's kind of like a lot, especially when you go to like more intensive applications, you might partition like on a timestamp field and based on your index. So there's a lot of considerations that you can do there and a lot of knobs that you can turn to really make the performance of your computations faster.
Awesome, thank you.
No problem. I do have a few more slides, but I wanted to just jump in and show you the Dask and Rapids example because I think that one's actually really fun. So I have this other demo here, and I have a video that we kind of recorded at Saturn. If anybody's interested in seeing it, but I'm not going to show you the Spark one. I'll show you the Scikit-learn one. So it's the same idea here, where we're loading some data. It's the same taxi data, and then we train this random forest classifier. So all this stuff was abstracted because I was running code a lot of the times, but you can see here that it's the same features that I was doing. In this case, though, I turned it into like a classification model, basically trying to predict if somebody was a high tipper. So did they tip more than 25% for the ride? That's kind of what we're doing here. So that's fairly straightforward, right? You kind of pull in your data, and then all it is to run the random forest is right here. So I would say, and with my n jobs equals -1 parameter, it's actually going to parallelize this to all the cores on my machine. So I think this machine I used, what did I use? I use a pretty big machine here. So this machine had 30 cores, 200 gigs of RAM. And I was training on, how much data was this? This is 60 million rows from the taxi data. And then it was able to train in 10 minutes. So that's not that bad, right? I mean, 10 minutes is 10 minutes, but it's not horrible. I did have to sample my data a bit. So you see I sampled it down to 30% of the original data. And this is one single model fit. So like a lot of the times in a random forest, you would try different numbers of trees. Like I tried 10, 20, 30, 100, 200. When you think about doing that grid search, now is when it's going to take a long time to do stuff. So the whole thing is like, you don't want to have to leave a model running overnight. You want to be able to like iterate on stuff quickly. So what I'll show you here is the Rapids code. So this is Dask with Rapids together. So I set up a different cluster. I think I have this on, so I think it should work. Yeah, okay, cool. So what I'm doing here is now I'm actually getting 20 workers of this Amazon instance, which is just an instance that has a single GPU on each node. And these aren't really like even the cool GPUs. These are like T4s, like older ones. You can get them with, Amazon has like V100s on there too. And then Saturn supports the V100s, but these are actually pretty cheap. So what's cool actually is this G4DNX large with a T4 GPU costs around 50 cents an hour when you're renting it on Amazon. This machine here with 200 gigs of RAM costs like $2. And I think 50 cents can buy you a CPU machine that has like 8 cores and 60 gigs of RAM. So if you think about that, this is actually pretty comparable in price to like a hefty machine that you would normally buy. So it's not really cost prohibitive to do the GPU computation. So in this case, I'm using this Dask QDF package, which is basically saying I'm using Dask to read Parquet files. In this case, it's a kind of different file format. And then on this point here is I'm pushing that to the GPUs in my cluster by converting it into a Dask QDF data frame. And so here I'm actually not even doing a sample. I'm doing 300 million rows. So a lot of data here. And then when it comes to actually doing the random forest classification, the API is very similar. You notice here I don't have that end jobs. Let me zoom in here. Sorry about that. I don't have the kind of end jobs parameter that I was showing you before because it already knows to kind of run this on the cluster. And so this fit now, and I'll actually run it for you live here. Just, oops, I guess I'm not running it for you live. Ah, okay. I got to run all these cells again. Because I re-initialized my cluster without, while it was still on. But we can jump over to the Dask dashboard while this is doing things. I think it'll take like a minute to execute. So now we can see here that it's actually doing like loading from Pandas, which is loading those parquets. The Dask data frame, again, is a distributed, just a bunch of different Pandas data frames. And then when I say turn that into a QDF, Dask QDF data frame, it's going to convert those into QDF data frames, which are on the GPU. Then it pushes that stuff now down to the GPU. And here, I think I was executing like some length command, right? Let's see where we're at now. So the length finished. Oh, here, I'm calling persist. So essentially, it's actually doing all of that stuff. And then it's going to load all of this stuff into my GPU memory. And I think here it's actually training the random forest model. No, not quite yet. But you see now, I'm kind of have like a bunch of memory. And this is all GPU memory. Like I have like 160 gigs of GPU memory occupied across my cluster. Let's see what it's doing now. Okay, it still did that persist, and now it's on the fit, and that just took 1 second. So that was actually fitting a random forest with 100 trees over 300 million rows over 20 GPU machines. So it's pretty cool. I can run that again and hop over here, but you're gonna miss it because it just takes 1 second. So that's when it gets really fun to kind of do this stuff, is you can execute on a cluster of GPUs.
That is cool.
Any questions on the GPU stuff? I have a couple more slides to go through, and then I'll be done.
There are some questions on the chat, but not GPU related, I would say.
Okay, I mean we can go through those questions too.
So I've seen Scikit-learn, XGBoost, LGTM, or what, the light gate stuff. Is that supported also, or? Yeah,
light GBM is supported.
Okay.
I'm not sure if it's supported with Rapids, but I know it's supported with Dask. It might be with Rapids. I'm just not sure off the top of my head.
Okay. Any other machine learning toolkits that are supported by Dask, or is that pretty much? I mean, those are the leaders.
Yeah. Out of the box, that's pretty much what it is.
Okay.
But like I said, it's actually, if you had other things, it's pretty flexible to where, you know, somebody could implement some sort of, you know, other thing. Like I was showing some of the TensorFlow and PyTorch stuff. I think there's some discussions about working on kind of more native, like distributed deep learning training as well using Dask. I know that we work on some of that stuff as well. Like I said, you can do it kind of homegrown by using that Dask delayed stuff. You kind of have to think about more about how to chunk your data and partition it. And then it gets more complicated, right, when you're doing your GPUs and your deep learning stuff. But there's definitely an appetite, I think, for doing more native, like TensorFlow and PyTorch. And so kind of keep an eye on that. I think that's cool.
Okay. Aaron, I believe I heard you say that with 2 cores, you get a modest improvement, and then with 20 cores, you just went over, you get a large improvement. Is there some kind of a threshold where, you know, it would be a really useful improvement to your system?
Yeah, and it's hard because, you know, the unsatisfying answer is it depends. Like it depends on your data, it depends on your workload. But I'd say, like, even on a laptop, if you think about most laptops, you know, laptops will have like 4 cores right now, right? Something like that, at least. Mine has like 8, I think. And at that point, like you're gonna get an improvement. I mean, even with 2 cores, yes, you're gonna get an improvement. Depending on what you're doing, it might not be worth kind of, you know, thinking about the cluster computing framework, you know, even though Dask makes it easy, but, you know, sometimes you don't want to bring in a new package, right? But when you're getting into like multiple, you know, like 4 cores or any more than that, I'd say it's definitely worth it. But it does depend on your workload. And I do actually have a slide about that.
Thanks.
Sure.
Aaron, I had just sort of a general question. I was asking, do you see significant latency when you're either reading or writing to shared memory? Are there sort of rules of thumb, like if you're accumulating a result or something? Or does it handle a lot of that under the hood, or any gadgets to look out for?
Yeah, that's a great question and a great thing to consider. I'd say that Dask handles a lot of things like that under the hood. It'll evict objects from memory when it knows Dask handles a lot of that. So, like, for instance, if I persisted this, if I persisted this object and then I would like delete another object above it, like maybe this you know, train thing, it would kind of remove all that stuff from memory. But yes, I mean, there's definitely going to be latency, right? It's a lot different when you have all of your stuff loaded into memory on your client machine. When you're operating in a cluster, mostly in a cluster, when you're on a single machine and parallelizing it, it's all kind of still there. When you're on a cluster, it is different boxes. So you are going to get some network latency. So there's actually some things that I've worked on myself where the latency wasn't worth it. But most of the time, that's not the case. Because in that, I think the example that I was doing there was where something you were dependent on some like external thing to happen. I think I was hitting some REST API and there was some latency with that REST API. So the latency that I was getting from the REST API for each of the individual objects, it was the same. It wasn't worth kind of distributing that because I was still waiting on all those distributed things anyway. But I'd say most of the time, Dask is pretty good at handling things for you. Another question here is, with 1 core, even the memory management would help. Yes, so that's a good point, actually. And so the memory management helps, but also what's cool is the Dask ML. I don't know if I have the documentation up anywhere anymore. The Dask ML grid search is actually really cool. Because if you think about how a grid search works, I'm not sure if I'm gonna be able to find the example. This grid search right here. Oh, that's a Scikit-learn one. Okay, but anyway, so if you think about a grid search, right, you're chunking up your data, and then you're just training the same model over and over and over again. With Scikit-learn, if you had a pre-processing pipeline, you would have to re-execute that pre-processing over and over again in each thing. Scikit-learn is kind of dumb in that respect. It's going to reprocess all that. But if you think about it, that pre-processing only happens, you know, a handful of times on each of your chunks. So Dask will actually figure that out, and then it'll persist those chunks with the pre-processed stuff, and then all it's doing is executing your model. We have some examples of that too. The hyperparameter tuning one is actually really, really compelling. Another question here is, Let me spend a few minutes on how Dask or Rapids can help with TensorFlow training and inference. So I would say that the most immediate and quote unquote like easier lift that you're going to get right now as Dask sits as its own open source project is on the inference side.
Mm-hmm.
So if you have a trained model, right, and you have like, let's say you needed like large scale batch inference, you could load up a Dask data frame with your data. And then you would essentially map your prediction. So you would just basically, it's, you know, I'm kind of talking theoretically, but you would basically tell Dask to run this chunk on this worker, and this worker has the copy of the trained model on it already, and it would do all of that stuff in parallel. That would be pretty kind of trivial to implement, I think, using maybe like the delayed functions or some of the other data frame methods. You can do the training as well. And like I said, there's nothing in the open source project currently as it sits that's kind of out of the box distributed training. I'd say it's probably coming because I know there's a lot of appetite for it, and you could do it by hand. You would have to kind of do kind of the Dask delayed type thing where you'd have to figure out how your data is being chunked and then figure out what chunks you would have to do with the training. I'd say I haven't spent that much time thinking about that, but I know that it's something that our clients are really interested in, so I will be, and so hopefully I can have an update on that for you soon in the next few months.
Yeah, to clarify, when you mean in inference, are you talking about the cluster, or can you do this in a single machine with multiple GPUs and CPUs?
Oh, absolutely, yeah, you can definitely do it. If you have a single machine with multiple GPUs, you can absolutely do it with Dask too. Dask has this thing called a local CUDA cluster, which will, let's see. This essentially, it'll detect all of the GPUs on your single machine.
Got it.
Yeah.
So there's, in TensorFlow, they have a whole set of APIs around data sets.
Yeah.
And one of the things they do to really run things fast when you're doing huge amounts of training with very large data sets is you're doing the fitting over on the GPU, and you try to optimize data preparation to feed into that, you know, batches into the model to do fitting on the CPU so it can work in parallel. And I can see a lot of value if your data prep on the fly is very, and this would be when you can't just have everything up in memory, right? So I can see a lot of value in Dask doing that data prep on multiple cores on the CPU side, while TensorFlow is handling the fitting over on the, you know, what a neural network or whatever over on the GPU side.
Yeah, absolutely. That's a great point. And we've actually done that with some of our clients.
Okay.
I can't go into details, of course, on like exactly what it is. But we've done exactly that, where a lot of the processing was using like Dask arrays. And then the deep learning training was happening on the GPUs. And then if you need to do like large scale scoring or inference, you can then also use Dask to do that, like on your multiple GPUs.
Yeah,
it's really fun.
One of the most painful things is when you have a lot of GPUs that are just idle waiting for that input data, right? So yeah.
Exactly. It gets really exciting when you can spin up like 80 GPU machines and watch them all doing stuff at the same time.
But David, that means that you have to figure out how to integrate the CPU parallel operations with the training. Is like you really have to kind of hack the TensorFlow way of doing things, or?
So what I'm thinking is more like, you know, when you do data sets and you do map functions,
yeah,
to prepare the data, you could use Dask inside of those functions, you know, and parallelize that prep work.
Got it.
Aaron, a quick question. When it's referring to Dask CUDA, I get a little confused by the documentation. Are those GPUs, don't they have to be bus connected? In other words, they can't be on different machines? That if you have multiple GPUs, that they have to be on the same PCI bus?
Yeah, in this example, for this local CUDA cluster, that's the case. But if you were to launch a cluster of machines that each, like different machines that had a GPU on them, Dask also supports that. Like it'll detect that you're actually running on the GPU. So like the example that I showed before, this is running in Saturn Cloud, and so we kind of have a lot of that optimized, like the under the hood stuff optimized. But this cluster, I mean, this is a class on top of like, one of Dask's cluster open source ones. It knows already that it's operating with GPUs.
Okay, great. One quick follow-up. So can it deal with asymmetrical GPUs? Like I have multiple GPUs, but they have they're different size memory sizes, but they're in the same compute category. Does Dask transparently deal with that?
So it should work. Some might be slower than others because they would get the even amount of data. But what's really cool, and I'm not going to be able to Google and find the documentation for you now. Maybe I can look for it later. But Dask actually has ways for you to tell it to only do certain computations on certain workers. So you can say, I have a cluster of 20 machines, but only one of them has a GPU. You can do all of your data prep stuff on the CPUs of those, and then you can tell it only this worker is the only one that gets the GPU code. I'll try and find that because it's pretty cool.
Thank you very much.
Sure, sure.
And a follow-up, I know Steve works a lot with edge devices like Jetson, NVIDIA Jetson devices. Would a library like Dask run on smaller devices like that, or does it require significant hardware to run?
It would require the same hardware that you would need for like Python packages. And so I'm not super familiar with edge computing myself, so I might, just take that with a grain of salt. If you can run like Pandas on it or something like that, you could probably run Dask on it, but there is like overhead to it. I mean, it's definitely not minimal. Like it, excuse me, when you're running on a cluster, you don't notice. Even if you're running on your laptop, you don't notice the overhead. But if you're running on an edge machine, you might notice the overhead then with Dask. But I'm not really sure. I don't know enough to answer that.
This wish trying to get in. I found like a few other VACs, like one of the example, where they can do all of this without using GPU, but they claim the same taxi data that you have. They can run it in less than 2 minutes on your local laptop. And I just pasted that URL out here. I was trying to compare if there are anyone like that.
Yeah, and actually, this is one of the things I covered in that talk where I'm talking about when in my data science long talk in a couple weeks. And I can see if I can pull up that slide. Actually, it's not that
fine. Is VAX another
yeah.
platform?
So VAX is a little different. VAX is it's pretty cool. Like I'll say, it's pretty cool. So VAX is not a cluster computing framework. It's an out-of-core data frame library. So the very first thing to know about VAX is that it only does data frames and some visualizations. So it's like, if you then needed to drop into doing like Scikit-learn and like all this other stuff that Dask covers, VAX doesn't do that. But VAX is pretty cool and pretty good at doing the out-of-core. So essentially it utilizes your disk, and it only loads chunks of data into RAM as it needs it to do stuff. And yeah, the example that they did was with the kind of New York City taxi data. And it's pretty cool and very compelling. So, but you're running that on a single machine, and then you're only doing data frames is the one thing that I would say. And it's a newer package, right? So Dask is pretty mature. It's been around for over 5 years. VAX I think has only been like a year. So when it comes to like doing a bunch of stuff, you might run into more edges with that. But that's definitely a great project to watch.
Thank you. Any other questions for Aaron?
Yeah, does Dask require anything else on their local machine other than having the GPU and CPU and memory? Because when I try to install, I'm getting a lot of errors.
Oh, really? Interesting.
Yeah.
Maybe you can follow up with me and like ping me with the errors that you're having. But Dask, you don't need a GPU for it at all, and it should pretty much install with a conda or a pip install. It'll install the dependencies that it needs. It's nothing any too heavy. I'm sure it needs like Arrow, and it'll need like this S3FS package and a couple of other things, but it should be able to install pretty well. So yeah, reach out and I can kind of help you out. So just going back to my slides, I know we're almost out of time. The slides are on GitHub. Like I said, the larger example that I showed, there's a video there and some more code for that. We talked about some of this stuff. This was kind of just my guide, is basically use your laptop and then use Dask on your laptop if that doesn't work, and then get a big machine and then get a cluster. Basically, it's just, try to stick to what you know until you have to. And you can kind of look at all this stuff later. This is a quick Saturn Cloud sales point, but anyway, thank you very much.
Cool. Thank you, Aaron. That was super interesting. I'm glad we're recording this session so we can review it later.
Cool. Yeah, and reach out to me on Twitter or email me, send me messages on the Slack if anybody has more questions.
Yeah. Yeah, people are thanking you online as well. Awesome.
Yep.
George, for organizing. Thank you, Aaron.
Thank you. Awesome. Thank you, Aaron. Thank you so much for stopping by, and really, really appreciate your effort and sharing with us this cool platform, and looking forward to learning more. If you learn more about the TensorFlow, any support with TensorFlow in terms of training or inference, please let us know. We're really interested in that aspect, and really interested also in exploring how can we parallelize the data prep that happens while the model is trained.
Yeah,
cool.
Absolutely. I will.
All right. Well, yeah. Thanks for coming by, everyone. Next week, Svetlana is going to be talking about open standards for machine learning pipeline deployment. So same time next week, and yeah, don't forget to jump on the Slack and participate and say hello. And it was really awesome to have you, Aaron. So thank you so much for coming in and speaking.
Thank you for having me. This is great.
Thank you. Thank you, Aaron. Thank you, everyone. Thank you, Lana. It was great. We'll see you next week.
Thanks, Aaron.
Bye, everyone. Have a good night.
Bye.